All right, good morning, good afternoon, good evening. So this is the asynchronous lecture for Stat 252 for March 19th. Okay, so this will be March 19, 21. What we're going to do in today's lecture is finish lecture set number 12. So we have 3 topics left in lecture set number 12. One of those 3 we started on Wednesday. So the first one is hypothesis about the slope of the fitted regression line. Okay, we can also think of this as, inference about the slope of the fitted regression line. So this would be the same thing as saying hypothesis testing about beta 1, confidence interval construction about beta 1. Following that, we're going to talk about 2 additional confidence intervals that we can utilize to make statements about a predicted value or the conditional mean of the distribution of interest. Now, before we review the first few steps that we see on the slide, on slide 30 in particular, I just want to quickly go over the rationale for this set of testing. So in this unit, our focus has been on fitting a simple linear regression model. Okay, and the simple linear regression model is shown in equation 1. So what we are saying is y is equal to beta 0 plus beta 1x plus some error term. If it's true that y and x have a linear relationship, then beta 1 should be a value different from 0. So you can imagine that if beta 1 is equal to 0 in equation 1, you then have yi equals beta 0 plus some noise, the epsilon. So that's basically saying the influence of x is negligible. It doesn't actually make any difference how x changes with respect to the value, with respect to the response variable, with respect to y. So there's no impact of x, the explanatory variable, on y, the response variable. So the purpose of the hypothesis test that we're looking at, in particular the hypothesis test about beta 1, are to search for statistical evidence to determine if there is actually a meaningful relationship between the explanatory variable and the response variable. So this hypothesis test is also called the model utility test, the test of no linear relationship, the regression t-test, or it's just a 2-sided test of beta 1 equal to 0. These are all the same thing, but the goal is also the same, to determine if there's statistical evidence that x and y form a meaningful linear relationship. Now, this particular hypothesis test utilizes the assumptions of the linear model. So this utilizes, or first we assume there is actually a linear relationship. So we can use a scatter plot to check this. That we collected a simple random sample of observations. This would come from some pre-established understanding of where the data was collected. And then that the error terms or the response values are normally distributed with constant variance. And we would evaluate this through residual analysis, which we talked about on Wednesday. And you will see examples of in the lab at the end of the week. The hypothesis test itself, so the 2-sided test of beta 1 equal to 0, is conducted in the usual 6 steps. The test statistic, which is shown on step 3, is a t-value, which means that we are using the student's t-table. Whenever we use simple linear regression, our degree of freedom is equal to n-2. We will see in lecture set 13, when we move on to studying multiple linear regression, the degree of freedom on the test statistic changes to accommodate for the number of parameters in the model. So instead of, for example, n-2, you have n-p, where p is the number of parameters in the model. But for now, it's easy enough just to remember that for SLR, the degree of freedom is n-2. But when we study MLR, multiple linear regression, you'll see the rationale for that 2 in the degree of freedom calculation. All right, we can also construct a confidence interval about beta 1. In the context of the model utility test, the interval can serve the same purpose. So if the interval does not contain 0, that implies that there actually is a usable slope, or rather that implies that there is a meaningful relationship between y and x. So the interpretation of the results is the same from the hypothesis test and the confidence interval. All right, so we are still working with the midterm mark versus sleep data set. In part A, we are conducting the regression t-test, aka the model utility test, aka the test of no linear relationship, aka the double-sided test of beta 1 equal to 0. So we have our 4 assumptions listed in 1A. Those again are the same 4 assumptions that we use when we fit the SLR model. So these have been verified throughout the lecture set. Again, for linearity, we use a scatter plot. For SRS, we need understanding of the material. For normality and constant variance, we use residual analysis. Okay, so the hypothesis test. On step 1, we have our null and alternative. For this particular test, it's a stock null and alternative. So it's always the two-sided test of beta 1 equal to 0. Step 2, significance level. Step 3, we compute our test statistic. Okay, so now on step 4, we can take either the p-value approach or the critical value approach. So if we take the critical value approach, we sketch our student t-curve centered at 0. Okay, so we have a t-value on alpha over 2. So this is going to be 0.025. And then we have n minus 2 degrees of freedom, which for us is 13 because there are 15 observations in this data set. All right, it's a two-tailed test, so we also have to consider the negative. Right, 13. Okay. So now we go to our student t table. We match 0.025 to 13, and that gives us 2.160. So negative 2.160 here and positive 2.160 here. Okay, and our test statistic you can see is much larger than the positive, so this is going to give evidence of rejection, which implies that beta 1 is different from 0, which means there is a meaningful relationship. Okay, if we take our p-value approach, zero. Okay, so we have t equals 7.745. It's a two-sided test. So we also consider negative t equals negative 7.745. All right. So our p-value will be 2 times the probability that t exceeds 7.745. So we go back to our student t table. We have 13 degrees of freedom in this case. Right? And then we can see that here is where our t-value would fall. So our t-value is larger than the largest listed value on the line, which means that the area in each tail of the student t-curve must be less than 0.05. So then we would have, must be less than 0.005, right? So this would be size less than 0.005. And this would be size less than 0. Okay, so since the probability that t exceeds 7.745 is less than 0.005, the p-value is less than 0.01. All right, so both approaches, it should be clear that we are going to reject the null. And then on step 6, so step 6, we actually have a lot of different options for how we conclude. The first part will be the same. So at the 5% significance level, the data provide sufficient evidence to suggest. Now we can say something very stock like to suggest that beta 1 is different from 0, but usually in this context, because the test is being used to evaluate linear relationships, so the usefulness of the line in some sense, or rather it's being used to evaluate whether or not there is a linear relationship between x and y. Typically the way we would conclude here is by saying to suggest that, and then we would say the explanatory variable, which in this case is the number of hours of sleep. So to suggest that the number of hours of sleep is useful as a linear predictor for midterm mark. Okay. So what we're saying is that the data has given us evidence that suggests that the number of hours of sleep is useful as a linear predictor for midterm mark. Okay. All right, so in part B, we want to compute the corresponding confidence interval, so the 95% confidence interval. So we're going to have T alpha over 2 comma n minus 2 is T 0.025 comma 13 is 2.160. Okay, then on step 2, oh, sorry, and note the assumptions are exactly the same here as they are in part A. So I'll just make a quick note of that. C A above. Okay, so on step 2, we have B1 plus or minus our T value multiplied by S over the, or sorry, multiplied by SE over the square root of SXX. So this is 5.902 plus or minus 2.160 multiplied by 6.710038 divided by the square root of 77.544. Right. Okay, so if we work this out, we should get 4.256 to 7.548. Okay, now there's a few things that we can take away from this interval. First, you can see that the interval does not contain 0. So because the interval does not contain 0, that implies that there is, or that we are 95% confident that beta 1 is a value different from 0, which means that, again, we have evidence that the number of hours of sleep is useful as a linear predictor for midterm mark. Now we can also just interpret this in a more direct way. Since we are talking about the slope, we can say we are 95% confident that for every 1 unit increase in the number of hours of sleep, the student's midterm mark increases by, or will increases will increase between 4.256 and 7.548%. Right, so we can interpret this result in the context of the actual problem. And in this actual problem, what we're trying to do is predict midterm mark, or predict, midterm mark as a function of the number of hours of sleep. So because this interval is an interval for beta 1, which represents the change in the midterm mark for each additional hour of sleep, what we are saying here is that we are 95% confident that if you sleep an additional hour, you will gain between 4.256 and 7.548% on the corresponding midterm. I just paused for questions. All right, so that's inference about the slope. And again, when we talk about inference about the slope in an SLR model, we're really focused on inference about beta 1, or we're really focused on beta 1 being different from 0, because that particular test has so much meaning in the context of what we are trying to do. That, again, that particular test is essentially telling us if the data suggests that y and x have a linear relationship, and if x is a useful linear predictor for y. Okay, there are two other confidence intervals that I would like to talk about in lecture set 12. They are called the conditional mean interval and the prediction interval. Now, the rationale for these two intervals: first, we established earlier in lecture set 12 that one of the main applications of the linear model is prediction. So we can take the model that we have fitted and use it to predict, for example, your midterm score given the number of hours that you slept. Now, we know, just like in any of our other inferential studies, that there is an error associated with the estimate. So the same way that we have an error associated with B1, the estimate of the slope, which we account for in the hypothesis test and the confidence interval, it follows that there is an error associated with the predicted value that we found using our regression line. Now, what's interesting is that, we can actually interpret this predicted value in two different ways. We can interpret it as a mean of the normal distribution that we expect to surround said value, or we can interpret it as an individual value. So if you reconsider the scatter plots that I've drawn a couple of times, well, the illustrations I've drawn a couple of times for the assumptional benefit, right? So let's say that we have our interval here, or there's our scatter plot here. This is the fitted regression line. Okay, so this is y equals okay. And then at some point on the line, you plug in a value, right? So x1 is just some number like 6. You plug that in, you get a point on the line. This point is believed to be the mean of a normal distribution. So we can interpret, in this point right here, this is the y hat, okay? So we can interpret y hat as being a individual value. So this is the score that I will get when x1 is equal to 6. So this is For example, on the slide, if I want to know your midterm mark, if you slept 4 hours, I plug 4 into the line, I get 62.83 out. So I'm saying if you, as an individual person, sleep 4 hours, my prediction is that you will have a score of 62.83% on the midterm. Now, given what we know to be true about the assumptions of the SLR model, it's also the case that when we plug 4 into the regression line, we are also saying that we are estimating the mean of this normal distribution that I sketched above to be 62.83%. So the 62.83%, the point that I have predicted when x is equal to 4, it is both the individual prediction for one person who slept 4 hours, and it's an estimate of the conditional mean of this normal distribution when x is equal to 4. So because there are two different interpretations, we can build two different confidence intervals for that point. And each interval has a different amount of error associated with it because of what it represents. Okay. So the first interval that we will look at is the conditional mean interval. So this interval on slide 33, or this procedure, uses the same assumptions that the SLR model uses. Step 1 is the same as it was for the confidence interval that we constructed for beta 1. But on step 2, we have our confidence interval formula. And in this particular illustration, y hat p is the conditional mean of y hat given x. Okay. So this is our estimate of the mean of that normal distribution when x is equal to some value. Okay. xp. So you can see that the error that we have to account for here is composed of SE, the standard error of the estimate, multiplied by the square root of 1 over n, plus xp, the value of x that we are predicting at, minus the mean of the x values, squared divided by sxx. Okay, and then we interpret the interval. All right, now let's take the same idea. So y hat p can be the conditional mean of the response variable at a particular value of x. But it can also be the individual predicted score for one person. If we consider that, so for the prediction interval, we now have the individual person. We have the same set of assumptions we had before. We have the exact same t-value. We again have y hat p, but now this is just one person's predicted value. Okay, so we have our t-value, then we have the standard error of the estimate again, multiplied by the square root. Now, what do we notice? This part is the same as the conditional mean interval. Okay. Now, the only difference is that we have the 1 plus right here. So what this is telling us is that the amount of error associated with the individual person is greater than the amount of error associated with the conditional mean at the same value of x. Now, the construction of the intervals will be very straightforward because all we have to do is utilize these formulas. But what is interesting is the interpretations that we get about this individual point. Because again, we can interpret it as the individual predicted value or as the conditional mean at x is equal to xp. Okay, so let's look at a couple of examples of computing these intervals. So in part A, we want to compute the conditional mean interval when xp is equal to 4. Okay, so we have little xp equals 4. The conditional mean is given by y hat p is equal to b0 plus b1 xp. So this is going to be 39.221 plus 5.902 times 4, which is 62.83. Right? So again, the conditional mean and the predicted value are found in the exact same way. Okay, so the assumptions here are the same as they were before, right? So we have linearity, SRS, normality, and constant variance. Okay, and we're using the same data set that we have used before. So we have verified these throughout the lecture set the same way that we did for the regression t-test. Okay, on step 1, we compute our t-value. So we're computing 95% intervals. So we have t 0.025, 13. And just like we showed before, this is going to be 2.160, right? So boom, boom, boom. Value is the same. So we have now y hat p plus or minus t 0.025, comma 13 multiplied by SE times the square root 1 over n plus xp minus x bar squared over sxx. Okay. So this is going to be 62.83 plus or minus 2.160 multiplied by 6.710038 multiplied by the square root of 1 over 15 plus 4 minus 5.52 squared divided by 77.544. So that's going to be 62.83 plus or minus 4.501481. And that gives us 58.327328 to 67.330. Okay, so now we can say we are 95% confident that the conditional mean midterm mark for all students that slept 4 hours is between 58.33 and 67.33%. Right, so what we're talking about here is the average score for every single student in the population that would sleep 4 hours the night before the test. So this is the mean score on that exam for all students that slept 4 hours. So somewhere between 58.3 and 67.3% on average. All right. Now in part B, we're going to compute the prediction interval. Okay, so the predicted value for a student that slept 4 hours is y hat p equals b0 plus b1x, which again is going to be 39.221 plus 5.902 times 4, which is 62.83. So not a fluke. It's the same value, the same number, two interpretations. In part B, we're interpreting the number as the individual score for each individual student. In part A, we were focused on it as a mean for all students that slept that amount of time. Okay, now the assumptions here will be identical to what we had in part A and for all of the material. So I'll just write C A. Okay, and then on step 1, we have our t value. On step 2, we have y hat p plus or minus t 0.025 comma 13 multiplied by se times the square root 1 plus 1 over n. Notice again, the only difference here is that we have 1 plus in the square root plus xp minus x bar squared over sxx. All right, so now we're going to have 62.83 plus or minus 2.160 multiplied by 6.710038 multiplied by the square root of 1 plus 1 over 15 plus 4 minus 5.52 squared divided by 77.544. Okay, so this is going to give us 62.83 plus or minus 15.17663. Okay, and then this is going to give us 47.652 to 78.006. All right, so that gives us 47.652 to 78.006. Okay, so now we would say we are 95% confident that the midterm mark for each individual student. Okay, so we're no longer talking about a collection of students. So in the for the conditional mean interval, we were talking about all students that slept the same number of hours. In this illustration for the predicted interval, we're talking about the individual student. So one student. So for each individual student that slept 4 hours, that student should score between 47.652 and 78.006%. Okay, so well, we have now seen the prediction interval, the confidence interval, and a complete assessment of beta 1 for the SLR model. A few notes to keep in mind going forward. The prediction interval is always wider than the conditional mean interval. Okay, so this is something that'll come up on the final and in the practice problems. So little trick questions that involve this idea. It's important to keep in mind that the prediction interval will always be wider. So the standard error for the prediction interval is always going to be greater than the standard error for the conditional mean interval. And again, you can see that here, the effect of the 1 plus changes the margin of error for the interval from 4.501 in the case of the conditional mean interval to 15.1766. So what we are showing is that the amount of uncertainty that surrounds the individual person is much greater than the amount of uncertainty that surrounds a collection of people. And this should make sense to us because throughout the course, we've seen how increasing sample size and increasing the amount of information results in a better estimate or a better approximation. So conceptually, this interval is reflecting that idea. When we use a simple linear regression model, we are assuming that fitting a linear model is reasonable. Again, it wouldn't be realistic to use an SLR model if X and Y did not form a linear relationship. So one of the first things that we want to do is check to see if Y versus X is in fact linear. When we fit a linear model to a data set, we can evaluate it in a variety of ways. We focused on the R-squared value, which is the coefficient of determination. And then we talked about residual analysis for assessing the assumptions. So in general, I think it would be fair to say that our assessment of the model does boil down to checking the assumptions of that model and making sure that there's no reason to, there's no evidence to suggest that those assumptions are not true. Finally, the test about beta 1, you can construct upper tail tests, lower tail tests. You can change the value from 0 to any other constant. So we could test beta 1 equals 2 versus beta 1 greater than 2. But in general, what we are most interested in is the test of no linear relationship. So beta 1 equals 0 versus beta 1 different from 0 because of what that means in the context of what we are studying. All right, so the material in lecture set 12 will be found on assignment 6. So about 50% of assignment 6 is for A6. So on assignment 6, we're going to study simple linear regression, which is lecture set 12, and multiple linear regression, which is lecture set 13. Lecture set 13, the multiple linear regression lecture set, is the final lecture set in the course. So multiple linear regression is the last topic that we are going to talk about. And the idea here is basically that you can form a linear relationship between a response variable and multiple explanatory variables at the same time. So in MLR, we assume y is equal to beta 0 plus beta 1 x1 plus beta 2 x2 plus beta k x k. Okay, and k can be any number, 3, 4, 5, 6, 7, etc. So you can have a very complicated model, or as a special case, you can have just the SLR model, right, which is shown right here. Okay, so the SLR model is actually a special case of the MLR model when k is equal to 1. All right, so this was a bit shorter of a lecture than usual, by about 10 minutes or so. So I apologize for that, but if you guys have any questions about the material, please let me know. Assignment 6 will be posted shortly, so you can get started on that if you're comfortable with the regression material. And I will send out some notes about assignment number 5. And if you guys have any questions about any of the material, please let me know, and I will talk to you on Monday.